Vassili Kolokoltsov is a professor at Lomonosov Moscow State University and major researcher at National Research University, Higher School of Economics, Moscow, Russia. He's also a professor emeritus at University of Warwick, UK. Professor Kolokoltsov got his PhD in mathematics from Moscow State University in 1984 and a full Doctor of Science in Mathematics and Physics from Steklov Math Institute in Russian Academy of Sciences in 1993. Vassili Kolokoltsov published 12 monographs and over 200 research papers in various domains of pure and applied mathematics. His research interests cover a wide spectrum of mathematical disciplines, including probability, stochastic analysis, optimization theory, game theory, differential equations, fractional calculus, functional analysis, mathematical physics, quantum control and games, mathematical modeling of socio-economic, ecological, and financial processes. During his scientific career, Professor Kolokoltsov visited and worked in various research centers in Europe and America, including the UK, Germany, France, and Mexico, and took part in numerous international conferences as speaker, organizer, or member of the program committee. He also has been serving as an editor in several mathematical journals, including Fractional Calculus and Applied Analysis and Dynamic Games and Applications. We're very happy to have you here. You may please begin your talk.
Well, thank you very much, Pavan and Arran, also for organizing this very nice sequence of events. So I'm very happy to be part of it. My lecture is entitled The Rates of Convergence of Continuous Time Random Walks to Generalized Fractional Evolution. So let me say directly that that was something a bit kind of unexpected to me, that these continuous time random walks, which started to flourish their theory, well, about 60 years ago, and it was then realized by physicists that the limits of this continuous time random walks are the evolution described by fractional differential equation, there was nothing about the rates of convergence. So, and therefore I started thinking about it because I thought this is a really very big and very strange gap. And it was clear for me also from the beginning that the intermediate step in this rates of convergence for continuous time random walks are the convergence for the functional central limit theorem with the stable laws limit, or with a kind of stable processes limits. So, and I started looking for the literature, then I realized that even in this direction, there was nothing done. It was for me the kind of second surprise. So that's the main point which I'd like to convey. So the first time rates of convergence for the functional central limit theorem with stable process as a limit, and rates of convergence for the central limit, for the functional central limit theorem for continuous time random walks. This is mostly, somehow I've done it mostly in some kind of inspiration step in last year. And so there is 3 papers where details of what I'm talking about today are presented. So I will start first with some, well, I indicate here this somehow 3 directions, which I already more or less indicated, but let me repeat them again. So the first step are the rates of convergence in the functional central limit theorem with stable limits. And I stress also that I'm doing here everything with explicit constants, which is not very often even in the literature on just stable limits. And then the main part somehow was the rates of convergence for continuous time random walks to fractional evolution. And well, the third part, which I actually planned to speak about initially, but decided later on that I will not touch it. These are the rates for Levy flights and Levy walks. So these are kind of possibly one can say applications, yeah, of these first 2 parts in more kind of physical, possibly terms. And moreover, there are some new interesting limit for the Levy works, which are given by not standard derivative, but fractional material derivatives. Okay, so these are these topics to cover. And also I want to mention another also point here concerning with the first part. I'm going to speak about some kind of limits which are can be called quasi-limits. That's the point is the following. Even from the beginning of the theory of stable laws, considered as the limits of some normalized sum of distribution, there was a criticism saying that, well, all distributions that we can meet in our world, they are after all finite. They have bounded domain, and therefore the limits of all normalized sums should be Gaussian. So there is really no place for this stable distribution in the limits of any real-world distribution. And so the point is, in fact, that, well, they talk about the large number. So they can be large, but not too large. So in the practical somehow applications of the central limit theorem with the stable laws and the limit, we actually talking about large n, but not too large. So if they are too large, then we really should fall into the Gaussian domain because, yes, everything is finite. But sufficiently large, and those large that we possibly can observe, they gives us this stable laws as the limit, not as the limit, but as approximation. And so with this my theory of explicit rates of convergence, this makes the story very clear. Well, for n in the range of this big to this not too big, yeah, we have can use the approximation of stable laws. And if n goes beyond, then we possibly can fall back to the Gaussian limit. Okay, so some contacts and also some references. And of course, as usual saying, this is not all reference that should be mentioned. There are quite a lot of papers here. So I'm just choosing some papers which are the most closely related to what I'm talking about. Yeah, so starting with the rates of convergence for central limit theorem, of course, the initial point is the classical central limit theorem, where we talk about the sum, normalized sum of independent random variables with the Gaussian limit. Yeah, so there is enormous activity, and I'm not reviewing this part at all. Yeah. Because, as I say, I'm more concentrated on stable limit and functional central limit theorem. So about them, there will be more words. So now rates for limit theorem with stable laws in the limit. Much less is known here, and much less papers are written, and these are some which possibly are the most related to my research. Shen and Zhu, especially, they have very similar range of assumptions, so to say, about distributions as me. Johnson, Samvers, Kuski, Keller. So these are papers which doing, say, they are doing rates of convergence for central limit theorem with stable laws. Yeah, so we're talking about the convergence of the normalized sum of random variables, such that they do not have second moment, but have power decay in their distributions. Oh, interaction. Well, then another group of papers. So, yeah, let me say that when we talk about approximating the normalized sum of certain random variables to stable laws in the limit, then these random variables can be characterized by two types of estimates. We can think about their distribution to be in some sense close to the stable distribution, at least in some large range of the parameters Or we can talk about the similarity or closeness of the characteristic functions. And these are different approaches, and it's often very difficult to relate results related to one kind of assumptions to another. So the papers which I mentioned in previous slide were really related to the way of assessing or estimating the closeness of a distribution in terms of the really distribution probability density function. And here is some list of papers when the central limit theorem with stable laws are approached with the assumptions related to characteristic function. And specifically, these two group of people, Klebanov, Rachev, Soferiani, they also attack well with the same idea in mind, as I mentioned you, with large n, but not too large n. Yeah, so they also give rates for some really scales, for some ranges of n, not going to infinity. And also I mentioned here some, well, it does not have the title here because there was not enough place on the slide seemingly, yeah? But this is some paper recent paper actually 2 years ago on astrophysics, where they precisely actually formulate the more or less the same idea with which I started, yeah? And everything is finite in our universe, therefore the true limits are Gaussian, but what we may observe is stable just because we're in the range of large, but not too large n. So this large can be, say, on the age of the universe, so it's quite sufficient for observing really the stable limits, which are in the sense of quasi-limits, yeah, and not the limits. Okay, so now what we know about the rates of convergence in functional central limit. So as these papers which I mentioned concerned the central limit theorem for distributions. And I'm moving in the direction of functional central limit theory. So if we consider functional central limit theory even for Gaussian case, then there is also surprisingly not too much known. So there is somehow fundamental paper of Borovkov of 74. There are some improvement recently, and there are nearby results, which you can find Antonio, Melbourne, Safuta, for some particular case of mixing with mixing property, again, of arrays of the sums, which really relates to the functional central limit theorem. And well, when we start thinking about convergence in the functional central limit theorem with stable limits, so as I mentioned, here stress again, nothing is known. So I'm really opening here the page for this new direction of research. Okay, and then now going to the second direction corresponding to really already continuous time random walks. So I also, so these are the definition which let me start with, yeah. So we have some scaled sum of IID random variables to begin with, yeah. Yeah, and then we take the inverse process NKH. So this inverse process, or another way, the process when this random walk reaches certain level. Yeah? And then we have some sequence of IID random variables xi, also possibly scaled in certain way, and we take the sum of this random variable, not a fixed sum, but a sum given by the inverse process to this random walk. So this is the basic scaled continuous time random walk, and in the limit it may converge to the evolutions which are described by time fractional differential equation. Yeah, so I'm just saying a bit in general words here, this kind of introductory parts, more precise things will be said later. So also, as I mentioned in the introduction, this whole paradigm, yeah, as I understand, appears somewhere about 60 years ago, or somewhere in the 60s of the last century. And there's quite a lot of activity of various extension of this convergence with non-independent possibly jumps, or position dependent, and so on and so forth. But amazingly, since then there was nothing about the range, about the rates of convergence. And that's this rates of convergence, which I'm going to present you in this talk. Well, I will firstly speak about this first part with stable laws, and then if I will have time, then I will turn to this continuous time random walk limits. Now, before going to details, also let me comment on on the importance of this thing. Well, I suppose it's clear somehow from general point of view. Yeah, if we have no convergence rates, then all our limits in practice are basically they have basically practically no value at all. So rates of convergence are crucial for any particular practical applications. And concretely, there is activity on numerical solution of fractional differential equations. So there's quite a lot on deterministic way, and recently just started to appear the paper on the probabilistic approach. And this probabilistic approach can be done directly via somehow probabilistic interpretation of the solution, but numerically much simpler is really to approach the solution of fractional differential equation via these continuous time random walks, which are much easier to simulate. And there are two papers which they were mentioned by, there was a talk by Professor Enrico Scala, so it's paper Enrico Scala and papers of Uchaikin Sayenko, which done basically this, they've done this work about estimation, but only with my results here, we can really speak about convergence rates of the numeric solutions, how really close they are to real solutions, these numerics which were given in these papers. So a first clear application of this rate of convergence are the activity around the probabilistic approaches to numeric solutions of fractional differential equations. Well, I already said there was some direction which I wanted to talk about. It's about Levy walk. This is a bit special example of continuous time random walk, but I suppose I skip even talking about it because I will definitely have no time for this. Okay, so now more close to the results which I'm going to tell you about today. Well, you see, I'm talking about the rates of convergence. So these are the distances. So the distances between distribution. Yes, I'm talking about always, I will speak about weak convergence. So the talk is devoted to the distances between distributions. So which distances between distributions I am going to use? So here is somehow the very general scheme, which is very useful in the context I'm using here. So CRD is a Banach space of continuous bounded function on RD. And suppose we have some subspace, which is a Banach space in its own, but with some different norm. Yeah? For example, this can be so once continuously differentiable function, or twice continuously differentiable function, and so on. So we can consider the following distance between the random variables. Well, better to say, of course, between their distributions. This is between their distribution. We consider supremum of magnitude of the difference of the expectation of function f sum over f, which has norm 1 in this B subspace of C, and supremum of these distances. So this is the well-defined distance between the distribution. So the mostly used example of this thing are, as well as I mentioned, B is a space of k times continuously differentiable functions, so function having continuous bounded derivative up to order k. And then these corresponding metrics, D, C, K, are sometimes referred to as the smooth Wasserstein metric. Yeah, and in fact, when K equals 1, then this one smooth Wasserstein metric coincides with the one Wasserstein metric by the famous theorem of convergence. Now, in my talk, it would be useful to go in a bit more detailed, so to say, distances, and instead of just functions continuously differentiable, we can consider the further continuous functions. So further continuous or functions having derivatives which are further continuous. Yeah, so this will play the main role, at least in the proofs of my result, which I will mostly formulate in terms of smooth distances, but these intermediate are important for the proof. Well, as I already mentioned here, that is H1, yeah, this is Wasserstein 1 distance, W1, and it is also Wasserstein C1 distance. They are all the same. Okay, so this is one way, and there is possibly one of the most effective, so to say, distances, at least for the one-dimensional distribution. These are Kolmogorov distances, which really estimate you the difference between the distribution function. Yeah, so this is a distribution function of one random variable, this is a distribution function of another random variable, and we take supremum, the magnitude of the difference. Well, there are analogs in multi-dimensional, but let me not mention them. Let's here concentrate on one-dimensional case. Now, turns out that one can estimate these Kolmogorov distances in terms of the this Wasserstein smooth distances. For this, we need that at least one of these two has continuous density. So that's the result that if y has continuous density, say py, then the Kolmogorov distances can be estimated in terms of these intermediate distances. Well, this h alpha, recall these are further continuous with index alpha. H1 alpha are functions which are differentiable, and their derivatives are further continuous with index alpha. Well, M is supremum over the densities. Yeah, so the derivation of this inequalities is, I suppose, rather standard. So, for example, for the case when we have here smooth functions, smooth Wasserstein distances, they are given in the paper of Chen, which I mentioned a bit above. Well, these are the versions with intermediate spaces, but the proofs are standard. Must present no particular new point here. Okay, so now let's go to results. Let me again remind you that I'm talking about two groups of results. One is the functional central limit theorem with stable limits, rates of convergence, and another functional central limit theory for continuous time random walk. So half of possibly the main part of remaining time, I will talk about this first part, and this first part is a necessary intermediate steps. This is the basis for the second. Hopefully, I will have a bit some time for the second part, but let's talk about the first part. So we can consider here now this scaled sequence of scale sum of IID real valued random variables. So I write here D1. So by the way, yeah, my results are for arbitrary D, and they are for beta from 0 to 2. So those beta which have natural probabilistic interpretation. But results slightly differ, especially for different beta. We have here different rates of convergence. So this is our scaled random walk, scaled H1 over beta. And this is a probability density P, which appears in the corresponding stable limit. In the next slide, I will describe the properties of this B. Yeah, and we will denote VHTH, the transition operator of this discrete Markov chain. Yeah, we can consider this as a discrete Markov chain. So what is about this P? So this is the probability density of each one of these two. So it should be similar to the stable one. So let's look at what we mean by similar. So if it would be AY minus 1 minus beta, so this is actually the stable part. Yeah? So about our P, we think that this is like that, but with some correction. So it's Y1 plus something bounded, Y minus 1. So this is correction. And again, important to say that very often in many papers which I mentioned previously, we assume this for big Y, so for Y larger than something. And here is some additional generality. Not for all Y more than something. We really consider some bounded interval of Y. So above BM, it can be even 0. Yeah, I just say that it's bounded. It can be even 0. Yeah, so if it is 0 above something, then we know that the normalized sums should converge to the Gaussian. And we are going to speak about here this kind of quasi-stable limit. Yeah? If this BM is infinity, then we are back to a real limit. Yeah? But I really would like to stress the possibility to have this intermediate cascading asymptotics when we have some part stable in some region of parameter and then Gaussian. So this is the main assumption, that this is the behavior in this interval, which is considered to be big. Yeah, in some sense, we have the estimates in terms of the powers of this BM. And well, it is bounded from the left, so it is 0 left than some minus B positive constant. And well, we also some additional small assumption is beta, BM, beta more than 1. This is effectively done to have that the integral of these things will not exceed 1. So this is assumption on P. And so what we want to show that this scaled random walk converge to the stable process well, generated by this effectively. Yeah? So more precisely, what will be our stable process in the limit? Stable process in the limit will be generated by this very standard form. Yeah? And you see, you have here this Y1 plus beta, Y1 plus beta 1. So this is the case when beta from 0 to 1. And this is a bit more longer expression for beta from 1 till 2. So we can denote T beta T is a Feller semigroup of the beta stable Levy process generated by this also standard object, of course, yeah, generated by this generator. And so what I want to assess is the deviation of our random walk with this limiting distribution. And this is the first result which I formulate here. Consider beta between 0 and 1 first. Yeah? Now our probability P satisfies the assumption which I showed 2 slides ago, which are effectively saying that they are on some big interval of Y, it behaves like Y minus 1 minus beta. Yeah? Okay, and then this, we are talking about the range of H, yeah, this small h, yeah. This is scaling parameter for the random walk. And again, if BM would be infinity, then this will be H just more than 1. Yeah? But this more than 0. But now they are not more than 0, we have some bound on the left. Okay, so then this we have this asymptotic. This is Markov chain of the random walk, and this is the Feller process, stable Feller process, and we have here the distance. So h, t, constant c0, and I write this c0 explicitly in terms of well, parameters which were introduced above. And so what is written here can be written in terms of the Wasserstein distance, because you see we have on the right here the norm of f Lip. Yeah, so this is actually about the distance in the Wasserstein 1 distance. So in the Wasserstein 1 distance, we have this very simple relation ht as 0 constant. So this is just for bit less than 1/2. If beta more than 1/2, then this estimates will become worse. Yeah, so h will be in a less, not just power 1, but a bit worse. Oh, well, there will be constant C1, also explicit, okay, lengthy, but it's still explicit. And again, we have the Wasserstein 1 distance, C here linear, and H in some part. Now, general, so this is somehow the basic pattern for the results, which I will show you later in other bit setting. Yeah, so beta more than 1, d more than 1. So some comments about this result here now already. So first of all, I'm pretty sure that these results are not optimal. Yeah? And that's what I'd like to say directly when we're talking about the rates of convergence. So the first step, of course, is to write some reasonable rates of convergence. Yeah, and the second step in all this kind of research is to try to find some optimal constant. For example, let me remind you the height, so to say, for the optimal Berry constant in the central limit theorem. It's a tremendous amount of activity to reduce this numeric constant from 7 to 4 and to 3 and so on. Yeah, so this is very natural activity in the fighting for the best constant. And here, as I say, this is not optimal. In the paper which I have written last year, I just really developed some methodology showing how these things can be derived, and I did not really struggle for the best estimate. So there is not about this constant, about these powers here. So, and also in the power which I'll show you in the next theorem, they all can be improved, and this is really one of the projects which I have in mind to develop further. This year I really have no time for this other project, but so just main message is that do not think that these estimates are optimal, they are final. Well, but at least they're explicit. And now also concerning this estimates, another also general remark. You see, we'd like to estimate it with requiring as less as possible regularity. Yeah, so here are two actually parameters, the power of h and the regularity of f. And they are somehow, each one is spoiling another. Yeah? So if we want to improve the power of h, then we have to decrease the regularity here. If we decrease, to increase the regularity. Yeah? If we decrease the regularity here, then we spoil the estimates for h. Yeah? So therefore, what is here optimal is, again, a question which was being considered, but it is not considered yet so far. Okay, and then also as a consequence, I mentioned to you that Kolmogorov distances can be bounded by the Wasserstein smooth distances. We get the estimate for the Kolmogorov distances between the distribution of the random walk and the corresponding stable process. Well, in case of beta less than 1/2, and in case of beta more than 1/2, you see we have here, while I'm talking about this functional, we really have supremum, yeah. So on the all the supremum over any finite interval of time. Yeah? But we have here this interval, they are not going neither to infinity nor not to 0, due to really to the essence of the random walks. small time random walks are not the same as the limit, of course. Therefore, here this is bound to 0, and we see how it spoils itself again explicitly. Now we can have some corollaries for sums. As you see, I mentioned that my stress was on the functional center limit theory, because this is a completely new topic. And convergence for normalized sums, there are results. But he was noting that if I reduce my functional result to just distribution, I still obtain new estimates. So so for, you see, the distances between normalized sum and the corresponding time-fixed parts of distribution of the stable process, so this is a stable distribution. And we have these estimates, and they do not, well, they, as I say, there are similar estimates in the paper of Chen, which I mentioned, that most closely related to this, but they still do not, they are still new. They are complementary. So even the application to the convergence of sums, seemingly the method which I am developing here gives useful result. Yeah, so here's a slide with some comments. I effectively already mentioned that the rates are not optimal. Now also, if BM, I also said it, but I can stress it again, yeah. So if BM is infinity, then we obtain really convergence rate, yeah. Once BM is not infinity, it's really some kind of quasi-convergence rate. There's no convergence at all, yeah. There's just distance between the distribution in small on some large range of n. Also, well, as I mentioned, results are close to the, if we reduce it to just distributional level, the results are close to the paper of Chen, but still they are new. Yeah, and they are new because I'm using, unlike paper of Chen, I'm using this intermediate spaces of Hurley continuous function, which allows for a better precision. And well, yes, as I say, they are definitely not final. Further improvements are possible. Well, now bit from 1 till 2. Nothing especially new here, just more notations. Yeah. So this was result for beta, previously result for beta less than 1. These are result from beta between 1 and 2. Well, we have the same assumption on P, but now the constant now should be a bit shifted from B, we turn to B tilde, which is certain mix up of previous constant. So there is some additional change of constant, but with this tilde thing, we get the result which is similar to previous one. All there is constant T, H in some power, and this constant T is somehow looks similar to previous one, depends on the tilde coefficients, bit and so on. Now you see we got what new we've got here, that in the previous estimates we have here F leap, and here we have F prime leap, yeah. So the estimate become worse. Yeah, we need, and this is a general thing, the larger beta, the worse will be the estimate. So they will require either more regularity of the function or worse powers of H. Yeah, so it's saying how we can choose in between here. If this is a question worth being considered to get some optimal thing here, but this is not yet done. Okay, so there are again versions from beta between 1 and 3/2 and between 3/2 and 2, slightly different powers. And you see when beta becomes closer to 2, then we already need Lipschitz second derivative. Well, now let's move to D more than 1. So it's very often, in fact, those papers are well right, one dimension. Sometimes the methods used are closely linked. one-dimensional assumption. So my methods are not linked with one dimension. So multi-dimensional will get basically the same thing, and even the formulation is the same. Yeah? So we consider the same random walks, but now with the random variables taking values in RD, and the distribution will be again this power, yeah, but now this is magnitude of y minus d. Now previously it was -1, now minus d minus beta. Again, y1 plus something small of the order y minus 1, and here goes some coefficient a depending on y bar is just the direction of y. And well, what we need is the integral of this ay with respect to this sphere, and we have bounds, some technical bounds. So now with this assumption, we'll get the same. This is now we look at the generator of the corresponding d-dimensional Levy process. You see here again y d plus beta instead of 1. And here this is a of y bar. Additional coefficients showing that we have somehow different magnitudes of different intensity of jumps, better to say, in different directions. Well, so here with one and the same index. Yeah, by the way, this beta and d, this beta also can be varying, and the method I'm presenting, they can deal with this case as well. Okay, so with this application, we have that the result are literally the same. It's literally the same, it's just the same, exactly the same estimate, which were previously, yeah? So all these estimates, they remain the same, yeah, where instead of a, we have to take this integral. And everything, yeah, this a. This is integral over this a over all these directions. Yeah, so for large dimension, we get exactly the same story as for one dimension. Well, we can concretely have a look at cascading asymptotics. So I keep saying that we have stable in some large but not too large regime, and then Gaussian for large. So here are some concrete examples. We take P, which is a power from y from 1 to bm some big number, and 0 outside. Yeah, so if we take normalized sums, we can see that eventually the normalized sum will converge to the Gaussian law. But in the intermediate thing, the part of n, they will converge to stable. So these are we can estimate now all the moments, mu, second moment, third moment. We need third moment to use the very estimate for the central limit theorem. And then we get this result, yeah? So we have distance between stable law, and this works for n less than this bm in power 4/9. And for all n, we have the central limit theorem estimates, and we see because of we see this is bm 1/3 here, and this is bm 4/9. Then we effectively see that this is intermediate regime. Yeah? For n less than bm 4/9, so we have stable, not limit, yeah, but we are approximate by limit, by the stable limit. And above this, we will get Gaussian estimates. And in between happens something unclear. There is some switching region where this stable asymptotics is transferred to Gaussian one. Well, method of proof, maybe I will not much. I have 15 minutes, so possibly I'll skip them, yeah. Method of proof are based on semi-group method, on comparing the propagators or the transition probability of Markov chains via comparing their generators. So in the paper which I mentioned, this detail can be found. And let me just skip it and say a bit, about now the really functional central limit for scale continuous time random walk. So this is second group of result, which actually I started with thinking about it and consider it's even more important because of this really fundamental role of continuous time random walk, which are playing now in the fractional calculus. So let me just formulate some results of continuous time random walks, and then I will finish. Yeah, so now we have tau I is the sequence of positive independent identically distributed random variables, which effectively measure the intervals, time intervals between the jumps. And they have probability density, which is like stable one. So it's continuously differentiable, and it has this stable form for large enough y, for some beta from 0, 1. So this tau E now will measure the time distances between jumps. So this is the corresponding random walk with which I have started. That was the first formula, continuous time random walk. But now it's really additional that this tau are positive. Because this will now we'll talk about times. But otherwise, it's the same as previously, and this VHTH is the transition operator of this Markov chain. And we define the inverse process as usual, or the fitting process. So NKH is basically the first time when the scale random walk touches the point K. This is a bit loosely said, because it may not touch it exactly, because this is a discontinuous thing, but the first time it crosses, it goes above. That will be precise. Now we have a sequence, another sequence, now RD valued of, again, ID random variable, and the distribution of each this XIH is given by some mu space. So the probability distribution in space, which depends on H. And we can consider this scale continuous time random walk as a random process defined in this way, as I already mentioned in the beginning. Now, under some conditions, this thing will converge to the semi-Markov process as described by fractional differential equation. Now, and for formulation, I take even a bit more general point of view. We'll look at continuous time random walk, which are position dependent. So really, the next jump depends on the position where we are. So to formulate this, we can introduce the OHN family of discrete time Markov chain, depending on this sequence tau E with some transition operator like this. But you see the new point now that the transition will depend on the position. And now we look at this OHTHH of X. So this is the more general version of what was written previously. And the new point is that each jump distribution depends on the position. So this is a generalized scaled position-dependent continuous time random. And well, we can take the inverse process to the stable subordinator, which will be the limit of this inverse process under the scale. So well, now it is known thing that if we scale this, take the limit of this scale random walk, then we'll get the if the process of just random walk after scaling converges to the fellow process, then this continuous time random walk will converge to the distribution of the time change Markov process, where instead of time, we take this sigma t inverse subordinate. And in fact, it will solve as the fractional in time partial differential equation. And so I'm providing you with the result about the rate of convergence. Yeah, so assume that we have this fella or adjunction. Yeah, we have the semi-group generated by our process. This process generated by these jumps without time change. Yeah? And we want that this process is semi-group is also semi-group in a domain D, which can be considered as a bound space itself. And these are some estimates for the approximation for UH and FH gains in terms of the norm of F. And then we have this result. You see, this is the distance between. So this is the distance between the distribution of this continuous time random walk and the time changed limiting process. Well, again, you see we have here explicit numbers everywhere. Yeah? Whatever it's written, and again, one sees that this estimate diverges for small time and large time, which can be expected. What is not nice here, of course, is logarithm. Yeah? So this logarithm is actually due to time, not space, not homogeneity of the underlying process. So in particular case, if m is 0, so if the limiting process is specially trivial, so the Levy process, then we get here power time of h, and this power again can be given explicitly. But again, as I mentioned, these are not, for the moment, optimal powers. Therefore, I'm not writing it in all situations. So, for example, some class of bit, I can write it here, but as I say, it's not very nice expression, and there is some work to be done to find possibly better these estimates. Yeah. Okay, so then the limit solved as this fractional differential equation, this Kaput-Barsham derivative, L is a generator process X. For example, we can take diffusion as the limit, or we can have stable process as the limit. And then as a domain, we can take a function, say 4 times differentiable, so that all estimates, all assumptions of the theorem will be satisfied, and therefore we have this convergence to this fractional differential equation when L is diffusion or stable process, for example. Yeah? But of course, we can take other here L and just the checking the corresponding assumptions like this one. Yeah, just require a bit more work. But for the diffusion and stable process, they are more or less well known, and therefore we get what we need here. So I think I told you most which I wanted to tell you, and this is a good time for me to stop. Thank you for your attention.
Thank you, Professor Kolokoltsov, for the nice lecture. For the questions, I asked the member of the audience to kindly raise your hand. Okay, I don't quite see any raised hands. So if somebody has any question or remark or something, you can unmute your mic. Probably no then. So I believe this is a good point to stop here. Thank you very much, Professor Kolokoltsov, for the nice lecture. It was very nice having you.
Thank you very much, Mehta.
Pleasure.
Nice to see you. Bye-bye.
Bye-bye.